Welcome to the CAI, the Trade Association for Content Delivery. This presentation is the copyright of the CAI and may not be copied by any means without permission of the CAI Board of Directors. The CAI was formed in 1978 as a not-for-profit organisation to represent all aspects of the signal reception industry, from the aerial installer to the manufacturer distributor and even transmission platform operators. It provides face-to-face training for the industry. It wrote the standards for the first NVQ in signal reception. It advises the industry on technology changes. It is the only body that has written codes of practice for the aerial industry, which cover trading as well as technical practices, inspects members for compliance, and investigates complaints from the consumer against its members. It consults with Ofcom technical committees and has identified reception risks. It sits on BSI committees, CENELEC and IEC and has major input on standards. It supports trading standards. It produced technical advice for anticipated LTE interference issues, and finally, its members are trained in safe working at height practices and have technical as well as commercial ability. Now that the analogue TV switch off is completed, the government are able to proceed with the next step of the process, the digital dividend, or selling off of the top end of the TV spectrum for mobile broadband services, better known as 4G or LTE. But this won't be without its issues, and interference will occur in a large number of aerial systems, be they single dwelling units, blocks of flats, or commercial premises such as hotels, schools, hospitals and so on. This presentation is to try and explain what measures can be taken to reduce that interference. The content of the presentation will cover the following areas. What is 4G or LTE? Delivering signal, the LTE issue, what has the CAI done, mitigation measures, rollout and the future. 4G, or fourth generation, is the next step in mobile communication. At present, most mobile phones use 2G and 3G. 1G was the very first mobile phone system using analog modulation techniques and was introduced in the late 1970s. But personal mobile phones have been around much longer, with phones fitting in some American vehicles as early as the 1940s. 2G was introduced in the early 1990s and used digital coding for improved audio quality. This was known as GSM, Global System for Mobile Communications. With improvement in technology, 2.5G was introduced and was termed GPRS, General Packet Radio Service. 2.5G led the way to 3G, which added multimedia services. Now we move on to 4G, which promises speeds up to 50 times greater than 3G, 3D virtual reality, high performance streaming of multimedia, increased interaction between corroborating technologies such as scan and pay from your phone or tell a car to warm up as you leave the house. LTE, or long-term evolution, is a standard for wireless communication of high-speed data for mobile phones and data terminals. It is based on the GSM Edge and UMTS HSPA network technologies, and it was at the World Radio Conference in 2007 when Europe and Africa were allocated the 800 MHz band and the Americas and Asia the 700 MHz band for these services. The digital dividend has enabled the government to move forward on their commitment to offer faster broadband to everybody, and 4G technology in the 800 MHz band has enabled this to happen. Everything Everywhere, a collaboration between Orange and T-Mobile, is already offering a limited 4G service at 1800 MHz. You can see here the full radio spectrum, with UHF TV in the UK currently taking up a band of frequencies between 470 and 854 MHz, channels 21 to 68, but extended to 862 MHz elsewhere. The TV spectrum is split down into further groups, and each group has aerials designed to perform at optimum response within it. The switch from analog to digital and final channel allocations not being known at the inception meant that the recommendation from Ofcom was to fit wideband aerials covering the whole of the TV spectrum from 21 to 68. This now means that the majority of aerials installed in the UK are designed to receive signals from 4G mobile base stations. Coverage for 98.5% of the UK population required 1,154 analogue transmitters, both main and relays. On top of this, some communities required self-help schemes where very low powered transmitters cover just a few properties. The main AT-DTT transmitters would only cover 73% of the UK, but in order to bring it back to the 98.5%, an extra 3 relays were required. But not all of the population can receive all of the services, and only 90.5% receive all 6 multiplexes. We now have to see what 4G will do to those figures. We are now in a position where channel 61 upwards is about to be sold off, and this is what the new spectrum will look like. The 4G spectrum is actually in blocks of 5 MHz width, but it is thought that to be economical they will have to operate in 10 MHz blocks. Either way, it doesn't make any difference to the scenario. You will notice that there is only a 1 MHz guard band between the end of the TV spectrum and the beginning of the 4G spectrum. Many transmitters will still be operating on channel 60, the ITV MUX from Oxford being a prime example. Between the downlink and uplink of the 4G services, there is a much bigger 11 MHz gap. We have already mentioned about the majority of UK aerials being wideband and will be prone to receiving signals from 4G base station masts. Here you can see a typical polar plot for a wideband Yagi aerial at 800 MHz. The normal practice would be to align this aerial so that maximum signal can be achieved from the DTT transmitter, but in places between transmitters it is not an uncommon occurrence to find signals from alternative transmitters being picked up on the side or rear lobes. Depending upon weather conditions, these signals may be strong enough to lock in and can create retuning issues by loading the wrong transmitter into the TV or set-top box. But it's not only other TV transmitters that can be picked up on these lobes. Any interference in band will be picked up, and even out-of-band signals may create a problem, especially if any form of amplification is used, Tetra being a good example. Traditionally, filtering has been a way to remove out-of-band interference. Of course, these interfering signals could just as easily be picked up by the main lobe of the aerial. Now let's look at a predicted 4G coverage for an urban area. You will see we have a 20 kilowatt DTT transmitter located some 20 kilometers away from the TV aerial, and a series of 4G base station transmitters, each with a coverage area with a diameter of 4 kilometers. Our TV aerial is looking straight through 3 2.4 kilowatt 4G transmitters, transmitting at a frequency that the aerial is designed to receive. Not only that, but transmitters around the periphery will also be picked up by the lobes of the aerial. Okay, this isn't to scale, but the principle is there. But the greatest issues will occur when the 4G base station is in close proximity to the TV receiving aerial, or TV reception is on channels close to the top end of the new TV band. For example, an LTE base station outputting 2.4 kilowatts at 800 MHz and 100 meters away from the TV aerial is likely to input 120 dB microvolt of interference onto the system. Peter Barnett of Mandacom was commissioned by Ofcom to produce a report on what may happen within a communal system. As part of that report, he carried out a test to see what happened to a DTT transmission that was subjected to an increasing level of interference from the 800 MHz band. To simulate the 4G interference, he used a noise generator in the frequency range 791 to 821 MHz, and to simulate 5 of the digital multiplexes, he generated noise between 682 and 714 MHz, channels 47 to 51. An actual DTT MUX was viewed on channel 37. All levels were initially set at the same value. The simulated 4G signal was then slowly increased and the effects noted. Here we can see the effect on the MER of the DTT multiplex on channel 37. Nothing much happens until a simulated 4G signal has been raised by 12 dB, and then the MER rapidly falls away. Remember, the minimum MER for a 64 QAM multiplex with an FEC of 2/3 is 23 dB. Now looking at a spectrum display, we can clearly see the intermodulation products coming in as the 4G signal is raised, which has the effect of crushing the DTT signals by as much as 5 dB. You can see initially the levels were set at 0 reference point, the blue line, and measurements were taken at 3 dB increments, ending up as the purple line with a 27 dB level increase. The CAI has also performed a very basic test to look at this problem. This slide shows a test bed we set up in our training room at Watford. It consists of 2 COFDM modulators, one set on channel 61 to represent one of the 10 MHz wide 4G transmitters, and the other set to channel 22, the lowest channel used for DTT transmissions from Crystal Palace. The output from the 4G transmitter was passed through a variable attenuator into a standard launch amplifier. The output of the launch amplifier was combined with the output of the DTT modulator and fed into a TV tuned to channel 22. The results speak for themselves. This is similar equipment set up on my dining room table. You will see the 2 COFDM modulators. The right hand one is tuned to channel 62 and feeds the launch amplifier via the variable attenuator. The full output of the amplifier is connected into a combiner, and the -20 dB test output is connected to a spectrum analyzer to monitor the level of interfering signal. The other modulator has a video input and is set to channel 22. Its output is connected into the combiner, and the combiner output fed to a TV also tuned to channel 22. And you can see the TV picture is quite stable. When we look at the spectrum display, and the only figure of interest here is being the actual level, all other parameters may be ignored, a level of 67 plus 20 or 87 dB microvolts, less the loss in the combiner, interfering signal at a frequency range of 598 to 606 MHz is being presented to the TV tuner along with the wanted DTT signal. Now let's see what happens as we turn up the level of interfering signal into the launch amplifier. Remember that this model simulates an aerial connected directly to a TV receiving a single DTT mux on channel 22 and interference coming in at the old channel 62. The only amplification used is to lift the level of that interference, so any problems that occur are in the TV itself. You can now see that the picture is starting to become unstable, with quite severe blocking occurring, and it is really quite unwatchable. And if we now look at the level of interference, we can see that it's been raised to 90 plus 20 or 110 dB microvolts minus the combiner loss. This slide shows a spectrum display of the lowest frequency used by a mobile device, a phone for example. Note the level of 18 dBm. In a 50 ohm system, this equates to around 125 dB microvolts of level. Now look at the interference generated in the 11 MHz duplex gap. Exactly the same scenario will happen between the base station frequencies and the top of the TV spectrum, and only 1 MHz of guard band has been allocated. So if this was in base station frequencies, then corruption would occur to DTT. Not only will 4G affect the tuner in the TV, but it may also affect any amplifier that is in situ by causing it to overload. Here we can see two common scenarios: a domestic system requiring some form of amplification, and the common consensus is that there are some 4 million households in this category, many of which will not be screened, and a basic IRS with no form of filtering on the front end. Both of these scenarios will be receiving and outputting signals up to 862 MHz. So that covers the background of 4G. But what has been done already, and what can we do to reduce the effects? The CAI has been involved through its technical committee with the digital dividend since the inception of the idea. A subcommittee was established to deal purely with the issue, making great use of independent consultants such as Peter Barnett and Brian Copsey. We have had a great deal of input with the government and Ofcom, not only in answering consultation documents, but also in face-to-face meetings with representatives from Ofcom, Department for Culture, Media and Sports, DCMS, and also Department for Business, Innovation and Skills, BIS. The CAI input to Ofcom was instrumental in getting them to look again at their computer modelling figures for the number of households affected. We are represented on BSI, CENELEC and IEC, and as such influence much of the standards that apply to the industry. We have also been involved with the European Commission workshops, which set up a joint ETSI-CENELEC working group on digital dividend interference issues. Distributors and manufacturers have been kept appraised of the changes and what to expect through seminars specifically for them, with members of government departments, Ofcom, DTG and the BBC in attendance to answer questions, whilst the installing member has had access to seminars at trade shows. We have also prepared information sheets that are downloadable from our website. The use of benchmark products has always been advocated by the CAI as best practice, and the change to benchmarked aerial design is going to be a very important part of the strategy in coping with 4G interference in the 800 MHz band. At a recent CAI seminar for manufacturers and distributors, with representatives from the DTG and BBC present, the possible change in aerial groups was discussed. You will see that the proposal is now for just two groups, the old Group A and Group T, to cover the new band from 21 to 60. T standing for total to differentiate it from wideband, and the suggested colour used to distinguish it will be white. By designing the aerial to cut off at 790 MHz will help mitigate 4G interference, but certainly won't stop it. Standard log periodic aerials will also not be a good idea for TV reception, as the response is so flat and doesn't tail off quickly. However, it is believed that some manufacturers are designing a new log periodic that will do this. In order to assist with the mitigation of the interference issues, the government has required the operators to set up a company called Digital Mobile Spectrum Limited, which has previously been referred to as MIDCO in Ofcom consultations and information. The remit of DMS is to solve interference issues on the primary set only, so if that set is served by satellite or cable, then it is deemed to be interference free and will likely not be covered. DMS will send filters directly to the consumer for self-installation, but the actual process of doing this has not yet been decided upon. It may be proactive and filters sent to everybody within an interference area, or reactive and sent out when consumers complain of interference. Where the filter needs fitting at roof height, a voucher scheme is proposed to pay an installer to do this work. But a word of warning, the filter sent out may not be suitable for outdoor use. The voucher scheme will also be available to the vulnerable. To assist with this, the CAI has made representation to DMS for its members to be the primary source for this work. The important point here is that currently DMS will not pay anything other than one filter per household and a voucher if a filter is needed in the rooftop aerial installation. So what can be done by the installer to reduce the effects of 4G interference? Some mitigation will occur at the base station, with filtering to reduce the amount of signal and any roll-off from the transmission. But that won't stop intermodulation products and amplifier overload causing an issue. Base station levels are expected to be high in aerial systems due to the fact that the majority of aerials, amplifiers and passives are designed to operate at these frequencies. So a single fix is unlikely. One simple filter will not solve all the issues in the majority of cases. A range of mitigation measures will be required. On top of that, multiple dwelling and commercial systems will likely require specialist solutions, as ingress may not just be from the aerial but could be at any vulnerable point further down the system, especially if the system is old or not installed properly. It is possible that 60 dB of rejection of the LTE base station signals will be required, with no more than a few dB attenuation of the DTT signals. All aerial systems, be they single dwelling, multiple dwelling or commercial, should be installed to certain standards, and the use of properly screened equipment is a must. Poor quality cable will allow ingress of interference to a greater or lesser extent, as will unscrewed amplifiers, splitters and outlets. Also, don't forget that many over-the-counter fly leads have very poor screening properties, and it may be better to make new leads from benchmark cable. Aerial and equipment location will also have a bearing on the amount of interference received, and moving the aerial or amplifier so that it is screened by the building will assist with this. Also, using an aerial with a narrow bandwidth where possible will assist, as will a use of filtering. It may be that a simple filter is all that is required, especially where TV reception is at low frequencies. So what new filters are available? Here we can see an idealised scenario. The red filter passes channel 58 with 3 dB-ish of slope and 50 dB rejection of LTE A, B and C. The green filter is frequency shifted to pass channel 59 and reject LTE bands B and C, but LTE band A to a much lesser extent. And the blue filter could be developed at a higher cost to pass channel 60 and reject LTE bands B and C, but would do little to stop band A. A filter to pass up to channel 60 and reject all bands A, B and C would be very expensive. Here we can see the spectral response for 3 different filters. The blue and red filters are very similar in what DTT signals will be allowed through, with a slope of around 3 dB across channels 59 and 60. The green filter has a slope of around 8 dB across the same band. When we look at the rejection of the 4G signal, you can see that again the red and blue filters follow a very similar path for the first 20 MHz. But very little rejection of these bands is evident. These frequencies will pass high levels of interference and offer little protection. Although the blue filter does offer more rejection in the last 10 MHz, it probably wouldn't be of much use anyway. The green filter is much better at rejecting all the 4G transmissions, but at the expense of channel 60. This filter should work well where DTT channels are below 59, and if the DTT levels are high enough, may even cope with an 8 dB loss on channel 60. As a final point, what would be the quoted rejection of these filters? Do the blue and green filters have a rejection of 35 dB? Well, yes they do, but only at a specific frequency, so it is important to understand what is meant by a rejection figure. Manufacturers already have filters on the market for both indoor and outdoor use. As already mentioned, DMS has been set up to administer and sort interference issues and administer the £180 million budget that is being provided by the mobile operators and government. Part of the remit of DMS will be to issue filters and, where appropriate, vouchers to cover the cost of fitting those filters. The value of the voucher is to be £50, and the government reckon something like 240,000 of them will need to be issued. But some systems may well already have adequate filtering. Passive cluster levelers will certainly have a great impact on 4G signals and should be all that is required to reduce the interference to such a level as not to cause an issue. Active levelers and channelized amplifiers, on the other hand, may or may not provide enough protection. It really all depends on the quality of the filter and its relation to the amplifier. If the filter has good characteristics and is before the amplifier, then it should work no differently to a cluster leveler followed by a separate launch amplifier. Here we can see that scenario with a schematic of an active leveler with 10 programmable filters followed by a split band amplifier. Just as with a cluster leveler, the fix will depend upon many factors, one of which is the amount of interfering signal hitting the input of the unit. It may be that an extra filter is required in front of the active filter or the cluster leveler. If a filter is used, it must be before any amplifier on the system. This applies equally well to multiple dwelling or commercial systems and single dwelling systems. If an amplifier is fitted on the mast, then the filter needs to go before it. You may think that, with a simple domestic system, where the aerial goes through a satellite receiver modulator, then into a DTT TV, the filter would go into the aerial socket of the TV. This may not solve the issue, as modulators tend to have an amplifier built in that would also be overloaded by the 4G signal. Fitting the filter in the back of the TV would filter out the unwanted 4G, but unfortunately the damage has already been done. The other consideration is when it needs to be fitted externally. Check that it is suitable, as some may well only be designed to plug in the back of the TV and will have no weatherproofing. Before we move on to other mitigation techniques, base stations are not the only potential source of interference. The actual handset could also create an issue, even though it operates at a higher frequency and lower power than the base station. Because it is operating much closer to the TV, a matter of a few meters as opposed to perhaps 2 kilometers, it could still cause an issue. This could be due to the fact that poor cable or unscreened outlets are being used on the TV system and the interference is being picked up on the system infrastructure. In this case, a simple filter fitted to the TV aerial socket may solve the issue. However, many TV tuners are no longer encased in metal and interference can be picked up directly by the tuner components. The only remedy here is to make sure the handset is not operated in close proximity to the TV or set-top box. Handset interference will not be covered under the government's mitigation scheme. In order to reduce the interference to a level that will not cause an issue, other techniques could be employed where just the filter has no effect. As we have already mentioned, aerials have side lobes, and it could be that the interference is being picked up on one of these. In much the same way as slightly moving the aerial off bore sight to reduce the effect of a ghost on an analog signal, a similar technique may be applied here. The beam width of an aerial is governed by the 3 dB power point. Depending upon the type of aerial being used, the aerial can be reorientated within its beam width so that the 4G signal falls within a null point between the lobes, whilst the forward gain of the aerial may only drop by 1 or 2 dBs. Changing the aerial to one with a different polar plot may have the same effect. But note that the nulls are frequency selective, and this may only work for relatively low levels of interference. Simply moving the aerial to a different location may also do the trick, either by causing the interference to fall within a null or by using the building to screen the 4G signal. If there is a choice of a different transmitter, then reorientating the aerial to use a transmitter with lower frequencies may be the best option. Any interfering signal can then be filtered out by using a filter with quite a gentle attenuation slope. The only disadvantage here is that many customers will not be happy with a change of local program schedules. Don't forget that proper installation practices are also required. Properly screened equipment, including fly leads. Properly made off and tightened connectors. Keep joins to a minimum. Remember, any joint is a potential for a fault, mismatch and interference ingress. Perhaps we should do away with equipotential bonding bars on switches etc. and bond directly to the body of the equipment. You need to attend the Making the Bond course to understand the full implications of this. Also, we mentioned that EE was using 1800 MHz for an early version of 4G, and this had the potential to cause problems in the satellite IF band. Using proper installation practices should solve this issue. And if all else fails, the customer may need a change of platform, either to satellite, cable, or in extreme cases via a self-help scheme to restore the DTT. Up to £10,000 per effective household has been allocated for this. So can I start fitting filters now? The recommendation is now, as the main problem is that many transmitters are still using channels above 60 for DTT and will be for many months. These are the predicted dates for switchover to channels below 60, but they are not set in stone. A total of 12 main transmitters and 70 relays. Of course, the other reason is that fitting a filter may not even solve the issue, and you could well be going back anyway. Should the customer decide that they want it doing now, it will be at their own expense, as DMS is unlikely to start sending out filters until a month or so prior to 4G deployment. So when does it all happen? As far as we are aware, this is the programme. Tenders will be received in December 2012, with a decision January-February 2013 and an announcement of the winners by March 2013. Then who knows? We reckon it will be the third quarter of 2013 before base stations start to appear in numbers, and full deployment will take 2 to 3 years. But there are many limiting factors: lack of handsets, governmental conditions for coverage of rural areas. We Are the First syndrome may result in limited coverage in large urban areas. Operator agreement on sharing base station sites. Base station availability. O2 and Vodafone using existing 900 MHz sites. Cost to the general public, in there are higher monthly agreements and handset prices. As the base stations start coming online, there will probably be very low deployment of terminal units, i.e. handsets. However, there will most likely be many scenarios where interference will occur. Unamplified aerial to one point. Indoor set-top aerials. Aerial amplifiers overload or amplify LTE signals. Communal aerial systems overload or amplify LTE signals. Communal aerial systems using locally modulated channels above channel 60 will suffer from very bad interference. Idle mode interference could affect 6 to 10% of TVs, and these could be a very long way from the base station. Idle mode is when the transmitter in effect goes into standby because there is no data traffic and keeps sending a data burst saying, "Is anybody there?" Some of these issues may be resolved as we have already mentioned. Individual TVs should respond to a filter, depending upon how close to the top end of the TV spectrum, but cable pickup may mean additional work will be necessary. Indoor set-top aerials, although the CAI would never advocate the use of such devices and would always recommend the use of a good quality benchmarked aerial fitted externally, may be able to be reorientated or screened from the base station to minimise interference, and the filter may help. Even external aerials may require these techniques. Idle mode issues may not be cured by inserting a filter, dependent on how the interfering signal is reaching the TV tuner, i.e. pick up on cable, fly lead, wall socket or direct into the receiver chassis. The fitting of a filter between the aerial and any amplifier may not be sufficient, as many amplifiers are unscreened and will suffer from direct pickup. In the first instance, DTT signal level checks need to be carried out to see if the amplifier is actually required, and if not, it should be removed. A level of between 50 and 55 dB microvolts should be aimed at for each TV, and don't forget that any filter will have an insertion loss that will need to be taken into account. If the DTT signal off the aerial will cope without the amplifier, removing it will help interference mitigation. If an amplifier is required to overcome cable loss or to drive multiple TV points, then it and its power supply must be screened. Communal aerial systems using locally modulated channels above 60 will need to reallocate such channels to below channel 60 and preferably below channel 56. As more terminal units or handset devices become available, the proximity of these to set-top aerials may create an issue. The same applies to poor quality cable in walls and fly leads. The proximity of the unit to the actual DTT receiver may also create a problem, as poorly screened tuners may well suffer from direct pickup, and distribution amplifiers could well be overloaded if close by. Where a large number of handsets are in use in one place, shopping arcades for example, the noise floor will be increased, and this too could well create interference and create issues for shops with TV displays running. As has already been mentioned, the CAI has never condoned the use of set-top aerials and would always recommend the use of a benchmarked external aerial. The fitting of a filter to a set-top aerial is unlikely to solve the issue, but moving the device away may help. The quality of the installation will also have a bearing here, as poor quality cable and unscreened outlets will be an important consideration to deal with this. Not an easy task in a shop with a large number of display TVs. As the main transmitters are installed, it will become obvious where there are pockets of poor service, and fill-in, Pico and femto cells will be deployed. These could be anywhere from public spaces to individual homes, offices and industrial premises. The effects will be exactly the same as the main base station transmitters and handsets. However, any work done to mitigate the initial problem may well need a re-evaluation, as these cells could undo all that work. And just when you thought it couldn't get any worse, we have other potential enemies to the installer. Weapons of spectrum destruction, otherwise known as white space devices, and talk of an auction of the 700 MHz band. Channel 38 has been allocated for PMSE, but whitespace devices can crop up all over the TV spectrum in supposedly unused channels. But many of these channels will be used for locally modulated programs in commercial premises. As yet, a method of solving this issue has not been finalised. The sale of the 700 MHz band will mean once again we have to look at aerial designs and reduce their bandwidth. But the ever-shrinking spectrum available brings us closer to the single frequency network, much like DAB. But that has other implications, such as regional news programmes. So how should we see this? Enemies to the industry and complaining customers, or opportunities for more work? Please send any questions to 4j@cai.org.uk and we will respond to them as soon as is practically possible.